So, have you ever looked at a massive piece of software, like a video game or a social media app, and just wondered, how in the world do developers build that without it turning into a complete and utter mess? Well, the answer lies in this really powerful idea called object-oriented programming, or OOP. And it's so much more than just writing code. It's a whole new way of thinking that brings order to chaos. I mean, seriously, think about the apps you use every single day. We're talking millions of lines of code. How do you possibly manage that kind of complexity? How do you keep it from becoming this giant, tangled knot that nobody can understand? That is the exact problem that forced a major breakthrough in how we write software. And that breakthrough is object-oriented programming. Instead of thinking of a program as just one long, endless scroll of instructions, OOP asks us to imagine our program as a world full of individual objects. Each object has its own data and its own special skills, and they all work together by sending messages to each other. All right, so how does this whole thing work? Here's our game plan. We're going to start with the absolute core building blocks, then we'll explore the four big ideas, the pillars, that give OOP its real power. And finally, we'll see how it all comes together to help us build way better software. Okay, let's dive right in with the two most fundamental concepts in the entire OOP universe: classes and objects. Seriously, if you can get the difference between these two, everything else is going to click into place. First up, the class. Now, it's super important to remember that a class isn't the actual thing. It's the blueprint. Think of it like the architectural plans for a house. The blueprint defines everything: how many bedrooms it will have, what kind of roof. Those are its properties or attributes. It also defines what you can do, like open a door, which we call its behaviors or methods. And if the class is the blueprint, then the object is the actual house you build from that blueprint. It's the real deal, a tangible instance. You can use one blueprint to build a whole neighborhood of houses, right? And each house is its own distinct object. One might be painted blue, the other green, but they both came from the same clan. This slide just nails the distinction. The class is the cookie cutter. It's the template. The object is the actual cookie you just baked with it. The class is the general concept of a bank account, but the object is Alice's specific account with her name and her $5,000 balance. One is the abstract idea, the other is the concrete thing. Okay, so we have our blueprints and our objects. Now, how do we make them work together safely without creating a huge mess? That brings us to our first two pillars of OOP: encapsulation and abstraction. These two are all about the art of hiding complexity. Encapsulation is pretty much exactly what it sounds like. It's about putting things into a protective capsule. You take an object's data and the methods that work on that data, and you bundle them together. This creates a protective barrier so other parts of the program can't just reach in and change things by accident. And why is that so critical? Because it makes your code incredibly robust and safe. It prevents one part of your program from accidentally messing up another. It also means you can completely change how a class works on the inside, and as long as you keep the outside controls the same, nothing else in your program will break. It makes maintaining code so much easier. This leads us right into abstraction. The perfect analogy is driving a car. You get a simple interface: a steering wheel, pedals, a gear shift. You don't need to know how the combustion engine works or what the transmission is doing to drive to the store. That's abstraction. It's the principle of hiding all that messy, complicated stuff and just showing the simple, essential controls you need to get the job done. It's all about the what, not the how. Now for our third pillar, inheritance. This is where OOP gets incredibly efficient. The idea is simple, but wow, is it powerful? Why build something completely from scratch when you can just take something that already works and add to it? Inheritance lets you create a new class. We call it a subclass or a child class that is based on an existing one, the base class. And here's the magic: the child class automatically gets all the properties and abilities of its parent. So for example, you could have a base class called mammal and then create a goat subclass that inherits all the normal mammal stuff, but you can also add its own unique goat-like behaviors. And you can structure this in a few different ways. You've got your simple, straightforward single inheritance. You can also build chains of classes, which is multi-level inheritance. You can have one parent class with many different children, which we call hierarchical. Some languages even let you have a class that inherits from more than one parent at the same time. The payoff for doing this is huge. You're writing code once and then reusing it all over the place. Not only is that faster, it's also way more reliable because you're building on top of code that you already know works. It saves time, it cuts down on bugs, and it gives your entire program a really clean, logical structure. And that brings us to our fourth and final pillar, which is probably the most powerful and, well, coolest concept in all of OOP: polymorphism. I know it sounds really complex, but its Greek roots tell you everything you need to know. Poly means many, and morph means form. One name, many forms. So in the real world, this means you can ask different objects to perform the same action, and they'll each do it in their own unique way. Think about telling a bunch of different animal objects to speak. A dog object is going to bark, a cat object is going to meow. It's the same single command, but you get many different results based on what kind of object it is. That is some serious flexibility for your code. Now, polymorphism usually shows up in two main ways. On the left, we've got method overloading. That's where you have multiple methods with the exact same name in the same class, but they just take different inputs. For example, a single add function could be smart enough to handle adding 2 numbers or 3 numbers. On the right, we have method overwriting. This happens with inheritance. A child class takes a method from its parent, but then it provides its own special version of it. So a general vehicle class might have a move method, but a car subclass will implement it by spinning its wheels, while a boat subclass will implement it by pushing through water. Same action, completely different behaviors. So we've covered the 4 pillars. Let's step back and look at the big picture. What is the real advantage here? Why did this way of thinking completely change the game for software development? This table wraps it up nicely. You've got encapsulation and abstraction, which work together to hide complexity and protect information. You've got inheritance, which is all about code reuse. And you have polymorphism, giving you that incredible flexibility. You can see they're not just 4 separate ideas, they all support each other to create this really elegant system for building things. And all of this leads to the ultimate payoff: reusability, which saves massive amounts of time; reliability, because you're building with code you already know is solid; maintainability, which makes life so much easier when you have to fix or update something later. And when you put all of that together, you get scalability, the ability to build truly massive, complex applications that don't fall apart. Ultimately, that's the real transformation here. You move away from that chaotic tangle of instructions, that one long list of to-dos, and you step into this organized world of objects that all know how to talk to each other. It's a system designed to mirror the real world, which makes it way more intuitive to build and understand. So, I'll leave you with a question to chew on. Now that you understand the blueprint, look at the complex systems all around you. A video game, a social network, a city's traffic control system. How would you start to design those things using